Professor Bauer is the chair of physics and astronomy at Michigan State University in East Lansing, Michigan. He got his bachelor's, master's, and doctoral degrees in physics from the University of Gießen in Germany in 1981, 85, and 87, respectively. And he served as the Department of Physics and Astronomy at Michigan State in various capacities, and has held various administrative positions, including chairperson of the Department of Physics and Astronomy and head of the theory group at the National Superconducting Cyclotron Lab, and director of the Institute for Cyber-Enabled Research at Michigan State. He's won numerous awards and honors, including an NSF Presidential Faculty Fellow Award, and he's a fellow of the American Physical Society. He's a renowned physicist and has widely served on scientific advisory committees all over the world. Okay, Professor Bauer.
Okay, thank you. I'm acutely aware that I'm the only thing standing between you and this. So I'll try to finish by 1 o'clock so that we can have lunch and then go. Much of what I wanted to say actually was preempted by Professor Sani in his very first talk. So I've been busy cutting slides from my presentation and then adding others to fill back. So what I'm trying to do is I'll try to contrast where conventional computing is right now, what we're doing, for example, in my institute, and then where quantum computing can compete as not as a toy model in a sandbox, but as a future general process computer, and that is going to be a hard order. So why do we need computing at all? And so I tried to make this sketch of complexity in many-body systems. So as the number of constituents goes from, well, 2 is the smallest, 1 is kind of pointless. So from 2 to infinity, the few-body systems are easily solvable with analytic methods, and you get things like wave functions like this, and in the large n limit you usually can neglect quantum mechanics at all, and you get thermal kind of descriptions that follow Boltzmann type distributions. Where the fun is in these mesoscopic systems in between, where computers become essential. We can use analytic guidance, but in the end we need to use computers. So I'll give you a very abbreviated history of physics as an example. So I have a timeline here, and in the 1700s, Newton invented calculus to describe mechanics. I say this as a German, and there's, Leibniz did it at the same time, but for mathematics reasons. So I think the valid reason was to invent calculus to describe mechanics. Then experimental heydays were in the 1800s, in the mid-19th century, where Faraday et al. Studied electricity and magnetism. I think then I can credit the German part of physics properly. In the early 1900s, in the early 20th century, Max Planck became the first theoretical physicist, and he became a theoretical physicist because he was locked out of the experimental lab by von Helmholtz. And then Planck and Einstein and so on explored the quantum world, and in the end of the 20th and the 21st century, computational physics emerged as a third branch of physics. I believe that's von Neumann there with one of those early difference engines. So there's this thing called Moore's law that has driven computer development over the last 40 years. Initially, Moore said 18 months, but now Moore's law has been corrected to say computer speed doubles every 2 years. If you look it up in Wikipedia, that's what it says now, but initially it was 18 months. Data storage, on the other hand, doubles every 12 months, and network speed doubles every 9 months. The physics limits in this are not reached for another decade, or more perhaps. So here's evidence for Moore's law. These are, I guess it helps to point the right side at the screen. So you see this is a doubly logarithmic plot. Date of introduction here is 1971, 2008. And then number of transistors in a CPU is a couple of thousand here, a couple of billion here. But a couple of billion, that's really cheating because these are all 8-core units. And so that's how Moore's law has been continued for the last 5 years. If you look at the CPU chips, the clock frequency hasn't actually risen anymore. It's, for the last 5 years, it has been 2.5 to 3 gigahertz, and that's it. So all the gains come from putting more cores into the same setup. And then eventually you run into the limit of heat. And for large installations, that's actually a limiting factor already. Right now, we're paying about half of the total investment cost in a large computer system is just in the air conditioning, not in the computing hardware. Here's the PC storage capacity. It doubles also every 2 years. So over the last 30 years, we had 13 doubling cycles. This is actually helped by new advances in physics. Now, any hard drive that you find in any computer uses principles of giant magneto-resistance, which were only discovered, 15 years ago, received the Nobel Prize 2 years ago. So here are the largest computers and their speed records from 1993 on to, well, I just downloaded it. This is the November 2009 list. You can find these at top500.org. And so the red graphs is the top performer on Earth, and the purple graph is the slowest machine in the top 500. So that's sort of the threshold that you need to get into the top 500. So the top machine on Earth that crossed the teraflop boundary in 1997 was ASCII red and then ASCII white. And then at least the US community received a big shock when the Earth simulator took the lead, the Japanese machine, in, 2002. And there was a huge investment in the US, and then Blue Gene took the title, and then there were a whole bunch of other machines that I have on the next slide. But the main point is that, in 1997, we crossed the teraflop, 10 to the 12 operations per second. In 2009, we crossed the petaflop, 10 to the 15 operations per second. And what would have been your world record machine here is now not even making it in the top 500 anymore by a long margin. So the top 10 computers in the world right now, is, in terms of floating point operations, are the Jaguar. It's a Cray machine at Oak Ridge. It runs at, I think, 2.4 petaflops. And then the previous world record holder was Roadrunner in Los Alamos. It's an IBM installation. And so on. You can see there's a German installation here at number 4. Number 5 is in China now. So, Japan is not on this scale anymore. So I want to highlight a few developments in the history of these computers. First, that they're driven by demand from the physical sciences and by invention in the physical sciences. So in 1946, the largest computer in the world looked like this. It was ENIAC at MIT, and it was all tube-driven and hand-cabled, as you can see, and it was filling this lecture hall. That's the kind of size that we were talking about. And people had definite ideas where computing could go from there. So this was electronic components that superseded the mechanical components, for example, of the difference engine. And that was the state of art in 1946. Now, in 1947, if you would have asked me to give what Vidal said is a vision talk, I would have said, well, this is the state of the art. And Moore's law actually held for these puppies too, just on a much smaller scale. And you could have extrapolated how computing will go, and you will have more and more tubes, and you will have more and more cables, and a bit larger and larger rooms. And probably this is going to be the end of computing, and then came along this little thing. So this was an invention at Bell Labs. It's the transistor. Bardeen and collaborators got the Nobel Prize for it. It was 1947, just a little over 50 years ago. In 2000, a threshold was crossed that there were 100 million transistors in each PC chip. I said in the last slide there were 2 billion in a PC chip now, but it's cheating because there's 8 cores. So the real figure of merit is something like 100 million. So over 50 years there was a factor of 100 million advance. Now, this was the best picture I could find of a large computer. This is Blue Gene. It was taken in 2004. This is racks and racks and racks and rows of racks and racks of computers. Blue Gene. And so the question is, can a little thing like this, a quantum computer that's in its infancy, do the same to this as the transistor did to this? So that's what we need to keep an open mind for. But let me just give you a first qualifier already. I think the CPU is actually not that important. The network is what's much more important. So let me talk about that. So as I said, it's more important than the CPU. This was the first sketch that I could find of somebody envisioning that one could network computers together. And it was the ARPANET, driven by the Defense Department. It was December 1969. It was 4 nodes. It was UCLA, UC Santa Barbara, SRI, oh yeah, Utah. Yeah. So that was the first vision of something which we now call the internet in 1969. So the whole thing became very, very useful in 1989, 20 years later, when the World Wide Web was invented by Berners-Lee at CERN, and this is actually the machine that he did it on. And in 1994, it all moved into the consumer domain with the writing of the code for Netscape, which was an old University of Illinois product, Mosaic, but written by the same person, Mark Andreessen, basically. And then, you know, it seems like Google has been around forever, but it was only founded in 1998 by Larry Page and Sergey Brin, 2 graduate students at the time at Stanford. So that's only 1998. And you see the invention cycles get shorter and shorter. Here it's 20 years, and then it's 5 years, and then it's 4 years. And the last thing that I'm going to put up there, what do you think should be the last thing that's going in this empty spot here? What's the new biggest thing that's even more important in Google? This, the iPhone. And you know, it seems like everybody has one of these now, right? This is a cheater's iPhone. It's only an iPod, but it does almost the same thing, except I can't make phone calls. And it's the first truly portable computer, and that was given into the hands of the masses, in particular developers. There's over 1 million apps right now that you can download onto your iPhone. And it was only invented in 2007, which seems like amazing. So the invention cycles get shorter and shorter, and I will actually come back to this idea of these shorter and shorter cycles in the end of my talk. So what do we use computers for? So what could quantum computing be useful for? I would guess, and you know, it's really risky to make these predictions, but anything on this page, quantum computing will never be useful for. Okay? So you could laugh at me just like the Thomas Watson quote that I will use later again 20 years from now. And if you laugh at me 20 years from now, that will be great, because that means quantum computing has been a success. And in addition, I am famous, because nobody laughs at the mistakes of not famous people. So I'm going to say it here, quantum computing will not be used of any of this, where we spend most of our time, you know, email, doing research, searching the web, spreadsheets, word processing, graphs, all that. Quantum computing will never have a use. I'm choosing my words carefully here. So some of us do actual programming, just like this, you know, this is a Java applet. And then there's advanced programming packages like Mathematica, Maple, MATLAB, that can actually be used for real research, for example, proving the Kepler conjecture, which could not be done by hand previously. Data collection, there quantum computers may be useful, actually. Not so much visualization. Visualization is already taken care of with incredible abundance, and you can see just some of these things that just pretty pictures. This is an interesting example, because that's research from one of my colleagues who works in the STAR collaboration at the Relativistic Heavy Ion Collider, and these people analyze in real time these events that consists of every one of these lines that you see is a track that a particle left, up to 10,000 particles. And now with the LHC switching on, this is going to be even a much bigger scale. So what do computers do? They enable science. So there's 3 high-tech buzzwords. Bio, of course, is very nano, and info. And I would say that the progress in bio and all biosciences relies on the advances in the nanosciences, and both are dependent on information sciences. So what we're doing at MSU is we have a high-performance computing center which works completely in a classical way. So we have 3 main setups, and they're basically commodity Linux cluster of maybe 1,000 cores. Then we have fab nodes that are 32 or 64 cores that sit on the same large memories, let's say 512 gigabyte. And we just bought these, so I haven't included them yet. And then also something that we just bought is a graphics processor cluster, which is also a new paradigm in computing that has nothing to do with quantum computing, but that uses the graphics processors that drive every screen in, for example, every PlayStation. And it turns out, just for the problem that you addressed of protein folding, these graphics processors are about 20 times faster than the conventional CPUs. They're very limited instruction set processor, but they're great for certain scientific applications. But I still would not call them a general process computer. So what's next for us is we also want to have a slice of the world record. So we formed the Great Lakes Consortium on Petascale Computing. And these are all the members. And interestingly enough, there's also even a couple of high schools in this consortium, and you can draw your own conclusions from this. And we have the Blue Waters machine, which will go online probably in 2010, but maybe only in 2011, and which will be the most powerful supercomputer on Earth. So what can you do with that kind of computational power? This is, for example, simulations that are done on the Earth simulator. So this is only 1/10 of a petaflop. And they're done by my colleague David Tomanik at MSU. And it's just some ab initio calculations of molecular forces that have a buckyball inside a bucky tube as a molecular switch, and here the merging of 2 buckyballs into a bucky peanut. So that kind of stuff can already be done, and we don't need additional computational power for that. Here's computational nuclear physics. I'm a nuclear physicist by training, so these simulations on this page are mine. And the questions that we're addressing is, how are the heaviest elements made in the universe? What's the equation of state of nuclear matter? We have a new experimental facility that will be built now and that the Department of Energy is investing 500 million into. And the computational tools produce output like this, where we can understand sub-nano, micro-nano, quantum system, nuclear collisions. We don't need quantum computation for that. We can simulate the quantum wave functions with semi-classical methods on conventional computers, and that works just fine. Computational astrophysics. So astrophysics doesn't have the luxury of doing. Here's a simulation that Ed Brown has done for surface waves on the surface of a neutron star. This is work of my graduate student, Terence Strother, and follows the isotope composition in a supernova explosion. The next highlight that I want to give you is computational biochemistry. So this is 2 of our faculty members. As part of their startup package, they got one of the top 500 computers in the world at the time, at 200 gigaflops. Now that doesn't make anybody's list anymore. But it was just basically a couple of closets full of blades like this. And as I said, more than half of the total expense went actually into air conditioning this room. And so one problem that I want to highlight is in the realm of protein folding, where you have to make, just like Professor Kak said in the previous talk, 3-dimensional structures out of a 1-dimensional coding sequence, which is a non-trivial problem. What they do is they use constrained molecular dynamics calculations. So one example is in the cholera protein, and there is this part of the protein acts like a piston to push out the cholera toxin. And these calculations that they do can actually predict the structure, and the active site sits here. And so in the calculation, you predict, you knock out this residue and you neutralize the poison. So that type of calculation informs experimental biochemistry on where to attack problems that are real problems in disease control. Here's a really interesting problem that, as a theorist, I like a lot. And it's from chemistry, and it's Piotr Piecok at MSU did this. And here's a very, very simple molecule, imine peroxide. It consists of a hydrogen, a nitrogen, and 2 oxygens. And experiments in chemistry were performed in 1998. 2 different experiments came up with vastly different answers for different observables for different coefficients in the energy function. And then the question is, here's one experiment, here's the other. They don't agree at all with each other. And these guys performed 4 sets of calculations based on these coupled cluster ab initio methods, which have turned out to be extremely predictive. And as a result of this, I just highlight one observable here, this the oxygen stretch mode. You can clearly see that all calculations agreed with one experiment and disagreed with the other. And so, on the basis of computational chemistry, it was decided that one experiment is falsified and the other is verified, which is just a total paradigm shift in science, because usually you did the other way around, right? You made 2 calculations, they disagreed, then you did the experiment to find out who's right. Now we can do calculations that decide which experiment is right. It's a paradigm shift. The next thing I want to highlight is digital evolution. So for the longest time, for the last 20 years, my colleague Richard Lenski has done very interesting experiments in microbiology with E. coli bacteria, where he grew these E. coli bacteria in petri dishes, and they multiply about every 20 minutes, so you get a new generation every 20 minutes. And then you can change some conditions for the E. coli bacteria. Let's say you change the sugar content, or you add some anthrax or whatever, and then you wait and see what mutates out of that. And every few hundred generations, he froze one generation away so that he had the ancestry. And then when there was an evolutionary trait emergent, he could go back and see how that originated. So he has on the order of 40,000 generations frozen away now. And then they tried the same idea with computer viruses. Instead of having biological bacteria, they used computer viruses that are the same kind of computer viruses that infest your hard drive and then you have to erase everything. Well, they infest hard drives on purpose for computers that are only made for this. And then they let them compete for space. And in some visualization, different colors means a different virus. You change the boundary conditions, you let them change their code by themselves and then replicate, and then whoever is the fittest wins. Now, this is called digital evolution, and it's many orders of magnitude faster than watching E. coli bacteria grow and divide. These digital organisms solve real computational problems. And so, again, this has nothing to do with quantum computing, but just like the graphics processors that I talked about earlier, it's a totally different paradigm as compared to conventional general purpose computing. What I predict is that these digital organisms will, for example, aid in drug discovery. So I'm one of the senior scientists on this proposal. We proposed this beacon, NSF Science and Technology Center. Eric Goodman is the principal. 2 months from now, we will hear if our proposal was successful. All that we know so far is that we're among 11 finalists for 6 science and technology centers. You can also compute with the internet as a whole, and so Seti is a good example. Seti at Home started the at-home boom. There are many at-homes now, but Seti stands for Search for Extraterrestrial Intelligence, and you can download a screensaver, and while your PC is not working for you, you're taking a break, your PC works for these guys. Typically what they get as a sustained rate, it's something like 60 teraflops per second. Without having to spend any money on machines, which is something like 1,000 CPU years on a conventional computer per day, just by harvesting the wasted cycle of computers worldwide. So let me give you an example from particle physics. A few days ago, really, the Large Hadron Collider at CERN produced its first particle collisions that are now the world record in collision energy, and it took that record away from the Fermi National Lab. So this is an aerial photo of Geneva. These are the Swiss Alps in the background, and superimposed is where the Large Hadron Collider is. It's 100 meters underground, so you can't see it, but that's where it is. It's Lake Geneva there in the picture. So let me just give you one example. The Atlas detector, the Michigan State group is a very active participant in this detector. There is no person built for scale, but it's about the height of this little shoe there. That's what one human being looks like in comparison to this detector. So this detector, at full luminosity of the LHC, which is nowhere near right now, but which will be reached maybe next year, maybe the year after next year, it will produce a lot of data. So it will produce collisions at the rate of 40 million per second. So it has a 40 megahertz duty cycle. That will produce 40 terabyte per second of raw data that have to be processed. So every second, 40 terabyte come out of this machine. And level 1, they have special hardware trigger that reduce this from 40 megahertz to 75 kilohertz. So they throw basically 998 out of 1,000,000 events, out of 1,000 events away, and keep 2 events that they have predetermined that are good. That gives you only 75 gigabyte per second. Then they have embedded processors in the detector, which reduce this data to 5,000, so a factor of 25, and 5 gigabyte per second. And then they have a dedicated PC farm really all across the world that reduces this to 100 hertz or 100 megabyte per second. And then this data storage and offline analysis is done by their tier 2 and 3 partners, and it will produce something like 10 petabyte per year. So if you assume that PC that you buy now, the upper end has 1 terabyte or so of a hard drive, that would fill 10,000 of those per year. So here's for several particle physics and nuclear physics experiments, the event size and the event rate, and the yellow ones are current ones and the white ones are future ones. And I put blue circles around the ones that MSU participates in. So Alice, for example, has by far the largest event sizes, which is a detector at the LHC designed for nucleus-nucleus collisions. So each one of their events has several 100,000 bytes. I already said that CERN plans to digest all this data worldwide. This is actually an old picture from 2004, and I couldn't find a new one over the last few days anymore. CERN computing is great, but not great with their visuals. So they have tier 1 centers in, I think by now, 15 countries around the world, and each country that has a tier 1 center, the tier 1 center for the US sits at Fermilab here, then has tier 2 centers distributed all across the country. And this is an old picture. I wanted to show that MSU and University of Michigan have a shared tier 2 center also, but this is too old. We didn't have one then. And then it goes to tier 3 facilities, which are usually not even drawn in except a few to any of the partners. While I have your attention, let me also talk about computers in teaching. That's something that should be considered here too. So a core business of any university, I would say, is the creation, application, and dissemination of knowledge. And in the context of this conference, I would just delete the word knowledge and replace it by information, which really is all there is, right? Information, creation, application, dissemination. So information technology, I hope, I have convinced you, has changed the way that knowledge and information is created in the physical sciences, and it will do the same in the way that information is delivered to students in the 21st century. So virtual university models are creeping up everywhere. Probably the most prominent one is the University of Phoenix right now, which is in the United States, the university with the largest enrollment of all universities and university systems. And it was created by a history professor who, in his mid-50s, who was just dissatisfied with how his students had to always go to his class instead of accessing them whenever he wanted. He's a billionaire now. Since the internet, I hope I've convinced you earlier, will have essentially infinite bandwidth, we have to rethink on how we deliver lectures. Like up there, there's the camera filming me right now. You don't have to sit in this lecture hall to get the benefit of what I'm saying. You can just go to the internet. But it has to be more. It has to be adaptive, immersive, and it has to be customized to the needs of the students, which is not what this camera does. This camera just films me and that's it. So learning environments have to be customized for the students. And then the brick and mortar advantages of having a place where students go will go away. And you know, you could say, well, okay, one of the points of going to the university is socializing. Well, when I gave this talk first, maybe 3 years ago, I did say that still. Now I'm not saying that anymore because I watch my children, how they socialize on Facebook. They are having 15 conversations going at the same time. They don't need to be in the same room anymore to talk to other people. The way that you interact in social settings has changed in ways that I have to say I don't understand anymore. So in any case, what one cannot afford to do is to outsource this information technology management to external commercial entities. And if the camera was not rolling, I would talk about Blackboard right now, but I'm not doing that. Fortunately, there is many approaches, and of course I'm only going to highlight our own. It's called LAN Kappa. It's content sharing across the net. It's customized content delivery for individual students, and it has a seamless internationalization. So there's actually, if you see the world map, the countries in red have multiple installations. In yellow, they have single installations. There is even one in India. And you know, you can just pull down a menu, you set your language to Hindu, and from then on the system delivers everything to you in that language. Portuguese is one, for example. Hebrew is one. Chinese is one. So this is all based on a Linux platform. It uses Apache web servers. Everything is in GNU public license. So participation in this is completely free. You just download a tarball, you install it on your local server, and then you're part of the network. You can use everybody else's resources, and if you want, everybody else can use your resources. Initially, we had set this up as an e-commerce platform where you could buy in and charge money for resources. But it turns out that people are just incredibly willing to give away their best stuff for free just for the pleasure of other people using it. So we have a library of more than 100,000 reusable resources. With resources, I mean a web page or a movie, an applet, a graphic, a homework assignment. So quantum computing, I'm coming to predictions here. So predictions are hard. So Niels Bohr said, prediction is very difficult, especially about the future. And I already mentioned that quote. It's maybe a misquote. It's not so clear that Thomas Watson Sr. actually said this, but it's just too juicy to let this go. So he was the IBM president, and in 1943, he's reported to have said, I think there is a world market for maybe 5 computers total. So it's still useful. Here's a quote that I like a lot. It's by Victor Weisskopf. He said, predictions are like Austrian train schedules. Austrian trains are always late. So why do the Austrians bother to print train schedules? Well, how else would they know by how much their trains are late? So here's some of my predictions. I would surmise that Moore's law will continue for at least another 2 decades. Why I cut this off in 2 decades will become clear in 3 slides from now. Network bandwidths will become infinitesimally cheap and eventually, also in about 2 decades, saturate the entire human input bandwidths. So in about 2 decades, we will be able to generate virtual environments that you can enter into, and you cannot detect with any of your senses anymore that you're dealing with a virtual environment instead of reality. There's a couple of cautions. Nathan Myhrvold, the vice president for future technologies at Microsoft at the time, he's not anymore, he founded his own company, he said software is a gas. That means software fills all the available space. The more CPU power, the more memory you give it, software will always find a way to fill all of that. And an indication of that is how long it takes for your computer to switch on, right? If you had computers 20 years ago, it took about 1 or 2 minutes to switch them on. It still takes the same time. And the reason why that is designers of software put more and more and more features into your hands, and there is a trade-off in more features versus, taxing the patience of the user. And for the last 20 years, that balance hasn't changed. So your computers become infinitely more powerful, but the waiting is still the same and still as frustrating. Caution number 2 is with all that growth in what the machines can do, the growth in content will only be linear, not exponential, because in the end, we still have to provide that content. So what does that have to do with quantum computing? So here's a quantum computer that our colleague Mark Dickman at MSU proposed, and it's just a proposal. There's no practical implementation yet, but it's a very elegant one that uses electrons on the surface of liquid helium. Now, so here's the basic promise of quantum computation. In conventional computers, you have n processors that can process n instructions simultaneously in some kind of time interval. Now, a quantum computer, on the other hand, with n processors, can process 2 to the nth instructions simultaneously. And so if you have 16 processors, it's not so great. 2 to the 16 is 65,000, so what? But if you double the number of processors to 32, then you get 4+ billion information units processed per time unit. So that's the great promise. Now, undoubtedly, the mathematics is beautiful. There are lots of concepts that were already developed in the early days of quantum mechanics in the earliest 20th century. The key ingredient is entanglement. That's what makes a quantum computer quantum instead of classical. Everything else is just window dressing. You have to establish a many-body wave function. And there's some surprising applications in a few algorithms, mainly database search and integer factorization. I had some slides here. I took them all out. Professor Vishal Sani just gave a perfect introduction, which I wish would have been 4 hours long instead of just the 1 hour that he used. But everything that you needed to know about quantum computing was in there already. But where is the experimental manifestation for large N? He didn't cover that. So let me address a few systems. Some of the candidates that have been proposed are, as I said, electrons on liquid helium, trapped ions. That's a graphics from and real data from the Vienna group, where they have 8 ions trapped that can be individually read out by lasers. Superconducting circuits, or SQUIDs, they're not exactly the same, but they both live on really cold temperatures, so I wrote them in the same line. Optical lattices. My colleague Carlo Piermarocchi is working on something that he didn't talk about here, but I think has great potential. NMR, which currently still holds the world record for the number of entangled qubits. There's BEC-based, diamond-based, cavity QED, a large number of experiments. One that I think is particularly elegant came out this year from the Yale-Waterloo-Vienna collaboration. It was in Nature earlier this year. And it has 2 qubits that are entangled via microwaves. And this figure proves that you can have entanglement on demand and that you have an experimental implementation of Grover's database search algorithm. So there are first, approaches in their infancy, just like the transistor was in 1947-48. But the big question is, can we really extrapolate this? So this error correction that Professor Kack talked in the last talk is one of them. Another one is really resolving structure. And so I tried to sketch this here. So can a general purpose, yes, you can have individual tailor-made tasks projecting a one-body wave function out. That's not a problem. But if you really want to have the process of quantum computing, this 2 to the n enhancement, you have to really construct a totally entangled n-body wave function. So I'm writing this like this, where the number of qubits are listed here, and it's a product wave function. I'm not even writing a Slater determinant. It doesn't have to be fermions, but it has to be entangled. It has to be a quantum mechanical wave function. And then you conduct some kind of measurement with this wave function. And when you do that, you get some observable. And so I plotted this observable in a one-dimensional scale. And for concreteness, let's say it's energy, which is probably what you will want in any case. So you can have a many-body wave function that is the entangled wave function of all these individual qubits. And if you want to do 2 to the n computations at the same time, you have to be able to project one state out. That's this red line out of the many, many, many that have some kind of observable in this space. Now, energy is probably the most convenient, and there will be a lower and there will be an upper bound. I mean, there wouldn't have to be an upper bound, but if there's no upper bound, you cannot perform a measurement. So for all things that you can measure, you have to have a bounded spectrum. And in this spectrum, you cannot have any degeneracy. Because if you have degeneracy, then you don't get single-valued functions out, and then your measurements will not yield a result that's unambiguous, which is also not acceptable, at least not for general-purpose computing. So you must fit 2 to the n discrete values, different values, into a narrow band, well, into a finite band. It doesn't have to be that narrow, but as n gets big, everything is narrow. And then you have what I call the Q factor problem. So the quality of an oscillator is, you can write as the energy divided by the absolute value of the energy uncertainty. And as n goes to very large, for n equals 32, I wrote earlier, you get already 4+ billion values. You have to fit 4+ billion values into this energy band, and then delta E has to be the difference between the upper and lower boundary divided by that 4+ billion. Okay, so delta E gets really, really small, and we simply have no physical way of making any physical system with that kind of quality factor. So that, for general purpose computing, that type of challenge is still far away from being solved, and only then can this promise of quantum computing really be borne out fully. So we're still far away from that. That's bad news and good news. If it was easy, then people would already be doing it. That's the bad news. The good news is there's really good work that one can still do and have a huge impact. In the last 2 minutes of my talk, I want to address this cycle of ever faster innovation that goes on in a more broad spectrum. It's one name for it is the Kurzweil singularity. What I plot here as an example is evolution of life on Earth. Okay, and so this is in million years. So here's 4.5 billion years before current time Earth was formed. And then it's not so clear when life developed, but somewhere in this ±1 billion year time interval. And then the first useful processes were photosynthesis, and then it goes on and it goes closer and closer. Animals only come into play about 500 million years ago. Land plants only about 400 million years ago. By the way, all fossil fuels that are presently exploited were made in a 100 million year band between the invention, when evolution invented plants with woodsy stems, and then evolution went ahead and invented bacteria that can eat that wood. In the 100 million years between those two time points, all the wood fell down and was accumulated and then made into fossil fuels after the plants died. And you see then it goes faster and faster, and by the time that humans arrive on this scale, you can't even see that anymore, it's so fine-grained. So again, evolution, inventions, so to say, progress in evolution went on faster and faster time scale as you go later and later. And so what you can do is you can plot the time difference between significant events, and you tell me what you call a significant event, and then I can compute the time difference in the past versus the time when it existed, when the event occurred. So here's the time difference is 1 billion years, and it occurred maybe 3.5 billion years ago. And here the time difference is only maybe 50 million years, but it only occurred 40 million years ago. So this is such a list of events. You can have any list that you want, and many people have compiled these lists. On our next slide, I show you many of them. And the result is pretty universal. You get a power law. And this is called the Kurzweil singularity. So here's a slide from Kurzweil. There's his newest book, The Singularity is Near, so I have done enough to plug his stuff. Ray Kurzweil, by the way, is the inventor of the synthesizer, and he has worked extensively aiding deaf people with his inventions. And he's also a futurist who thinks about these things. And I guess in this book by Modis, there was a compilation of other people's compilations of significant events, and there's a whole bunch of them. And what Kurzweil did is he just plotted them in the way that I just addressed, and you can really see that there is a power law, and you know, the time difference between significant inventions is between, or events is between 10 and the minimum now 30 years, and you see it crosses here in about 10 years or so. So no matter what significant event you have, earlier I had the network, right? How it evolved from the first DARPA scaling to the iPhone. And invention goes faster and faster. So that would also fit on here, except it would only fit in the last few, in this corner. No matter what you do, this Kurzweil singularity will be reached. What Kurzweil thinks, what I may or may not agree with, is that at the singularity, machines will actually become self-aware and will then have intelligence that far outstrips our own. If quantum computing can contribute to that, or if quantum computing will be obsolete before that arises, well, that's the big question. And I thank you for your attention.